Multimodal logic is a generalization of modal logic that allows for several different modal operators instead of just one. In standard modal logic, we usually work with a single necessity operator, the box, and its dual possibility operator, the diamond. Multimodal logic expands this framework by introducing multiple modal operators, each representing a different kind of modality. For example, a language might contain operators such as box 1, box 2, and box 3, each corresponding to a different accessibility relation or interpretation. One operator might represent knowledge, another obligation, and a third temporal necessity. In this way, multimodal logic provides a flexible framework for modeling systems in which several kinds of modality interact. Multimodal logic should therefore be understood abstractly as a family of systems rather than a single specific logic. Different systems arise depending on how many modal operators are included and what rules govern their behavior. The primary motivation for multimodal logic comes from the need to analyze situations involving multiple interacting modalities. In many areas of, for example, philosophy, linguistics, and computer science, it is not sufficient to represent only one type of necessity or possibility. For instance, in epistemic logic, we may want to distinguish between the knowledge of different agents. In deontic logic, we might distinguish between different kinds of obligations. In temporal logic, we often need operators for past and future time. Multimodal logic allows us to represent such distinctions explicitly. Another motivation comes from the desire to model complex systems in which different relations between states coexist. For example, in computer science, we may want to represent both temporal transitions and informational accessibility relations within the same formal framework. The syntax of propositional multimodal logic extends the language of propositional logic by adding multiple modal operators. Formulas are constructed from propositional variables using standard logical connectives such as negation, conjunction, disjunction, and implication. In addition, the language contains modal operators, box 1, box 2, ... box n. Each of these operators has an associated dual possibility operator, diamond I, which can be defined as not, box I, not. If A is a formula, then expressions such as box 1a, box 2a, and diamond 3a are also formulas. These can be interpreted informally as statements about necessity or possibility relative to different kinds of accessibility relations. The syntax itself does not determine the meaning of these operators, that is provided by the semantics. The most common semantics for multimodal logic is possible world semantics, which generalizes the semantics used in standard modal logic. A multimodal model consists of a set of possible worlds together with several accessibility relations. Each modal operator, box I, corresponds to its own accessibility relation Ri between worlds. Intuitively, the relation specifies which worlds are relevant when evaluating statements involving that operator. The truth condition for a modal formula can be stated informally as follows. A formula, box I, A, is true at a world W if, and only if, the formula A is true at all worlds that are accessible from W via the relation Ri. A formula, diamond I, A, is true at a world W if, and only if the formula A is true at some world that is accessible from W via the relation Ri. If we are dealing with multimodal temporal systems, we can talk about moments in time instead of possible worlds. Different modal operators may correspond to different kinds of accessibility relations, such as reflexive, symmetric, or transitive relations. By imposing constraints on these relations, one obtains different multimodal systems. Logical consequence in multimodal logic is defined similarly to that in other modal systems. A formula is valid if and only if it is true at every world in every model satisfying the relevant semantic conditions. Because multimodal logic allows multiple accessibility relations, the structure of models can be quite rich. Validity therefore depends on how these relations are defined and whether additional axioms restrict their behavior. This flexibility allows multimodal logic to capture a wide variety of logical systems within a single general framework. Several proof methods have been developed for multimodal logic. Among the most common are Hilbert-style axiom systems, which include modal axioms and rules of inference for each modal operator. Natural deduction systems, which contain introduction and elimination rules for the various modal operators. Sequent calculi, which organize proofs using sequence that track assumptions and conclusions. Tableau systems, which attempt to construct countermodels by systematically exploring possible worlds and accessibility relations. Labeled deduction systems, where formulas are explicitly associated with particular worlds in a model. These proof systems often extend techniques from standard modal logic while accommodating the presence of multiple modalities. Multimodal logic serves as a flexible framework that can be extended in many ways. One common extension involves introducing interaction axioms that describe how different modal operators relate to each other. For example, one operator might represent knowledge, while another represents belief, and special principles may govern their interaction. Hybrid logics, dynamic logics, and provability logics can also be viewed as specialized forms or extensions of multimodal frameworks. Propositional multimodal logic can be combined with predicate logic, leading to quantified multimodal systems. In such systems, we retain modal operators but allow quantification over individuals using variables, quantifiers, and predicates. This combination greatly increases expressive power. It allows us to represent statements such as, "Every individual could have believed that the Earth is not flat," or "Some agent knows that it is necessary that 2 + 2 = 4. However, the addition of quantifiers also raises new issues concerning domains of quantification, identity across worlds, and the interpretation of variables in modal contexts. Several familiar modal systems can naturally be understood as multimodal logics because they involve more than one modal operator, each associated with its own accessibility relation or interpretation. Here are some examples. Temporal logic. Temporal logic typically includes several modal operators representing different temporal relations. For example, operators such as f, sometime in the future, g, always in the future, p, sometime in the past, and h, always in the past, correspond to different temporal perspectives. F and g and p and h can be interpreted using two different accessibility relations between moments of time, one future-directed later than and one past-directed earlier than. Because multiple modal operators are present, temporal logic can be viewed as a multimodal system, multipersonal, epistemic, and doxastic logic. In epistemic logic, the logic of knowledge, and doxastic logic, the logic of belief, we often model the informational states of several agents. Each agent I has its own operator, such as K, I, agent I knows that, or B, I, agent I believes that. Semantically, each operator corresponds to its own accessibility relation, representing the worlds compatible with that agent's knowledge or beliefs. Since the system contains many such operators, one for each agent, it is naturally a multimodal logic. Epistemic doxastic logic. Some systems combine operators for both knowledge and belief, such as K, it is known that, and B, it is believed that. These modalities typically obey different logical principles and correspond to different accessibility relations. Because the logic includes at least two distinct modal operators representing different cognitive attitudes, it is again a multimodal system. Alethic or alethic deontic logic. A system combining alethic modality, necessity and possibility, with deontic modality, obligation, permission and prohibition, also forms a multimodal logic. For instance, the box may represent metaphysical necessity while O represents obligation. Each modality is interpreted with its own accessibility relation, one representing possible worlds in the metaphysical sense, and another representing normatively ideal worlds. The coexistence of these operators makes the system multimodal. In all these cases, the systems extend the modal framework by introducing multiple modal operators with different interpretations, which is precisely the defining feature of multimodal logic. In a multimodal system, we can describe how different modal operators relate to each other. Here are some examples of multimodal principles that can be symbolized in a multimodal system, but not in a system that only contains one kind of modality. If it is metaphysically necessary that A, then it is natural necessary that A. If it is physically possible that A, then it is metaphysically possible that A. If A is true, then it was always the case that A will be true. If A is true, then it will always be true that A was true. If the agent A knows that B, then A believes that B. If the agent A believes that B, then A knows that A believes that B. It is obligatory that A only if it is possible that A. If it ought to be the case that A and B is a necessary condition for A, then it ought to be the case that B. Many multimodal logics have well-studied metalogical properties. Depending on the system, they may enjoy properties such as soundness and completeness with respect to certain classes of possible world models. Some systems also have the finite model property, meaning that any formula that is not valid can be falsified in a finite model. The decidability and computational complexity of multimodal logics vary widely. Some relatively simple systems are decidable and computationally manageable, while more expressive systems, especially those involving quantification or complex interactions between modalities, can be significantly more complex. Multimodal logic generalizes the ideas of modal logic by allowing multiple interacting notions of modality. By introducing several modal operators and corresponding accessibility relations, it provides a rich and flexible framework for modeling a wide range of phenomena in philosophy, linguistics, computer science, and mathematics, etc. Starting from propositional multimodal logic, the framework can be extended in many directions, including quantified systems and combinations with other logical theories. Because of its versatility and rich mathematical structure, multimodal logic is an important area of research in contemporary logic.